Hello. Today we will be presenting our midterm project on the implications of beam geometry on spatial resolution in CT. Our objective today is to compare fan beam and parallel beam geometries in terms of sampling density and magnification, spatial resolution uniformity, especially analyzing the center versus the edge of the image, and reconstruction accuracy and aliasing behavior. We will examine how beam geometry alone, independent of filters, drives spatial resolution differences across the field of view. First off, we will have an overview of beam geometries, comparing parallel beams and fan beams. As you can see, parallel beams are equally spaced X-rays and they provide uniform sampling. The geometry is uniform, but it is slow. And on the right, we have fan beams, which are efficient, but introduce spatial non-uniformity due to the rays diverging from only one source. And as you can see here in our illustrations, you can see how the rays move across the object of interest. Next, we will discuss the geometric relationships and how they impact beam geometries. The first formula we see is magnification represented by the SDD over SOD. To explain further, moving the detector farther from the source, increasing source to detector distance, in this case SDD, or moving the object closer to the source, decreasing source to object distance, SOD, both result in higher magnification. In the second formula, we see effective sampling modeled by delta X ISO equal to delta D over magnification. Delta X ISO is equal to the sampling interval. Delta D signifies the detector pixel size, which is fixed, and the M signifies magnification, which depends on geometry. In our simulations, we can observe how magnification governs both resolution and blur. Increasing SDD, source to detector distance, or decreasing SOD, source to object distance, improves central sampling but amplifies peripheral blur. The bottom image shows increasing SDD, source to detector distance, or decreasing SOD, source to object distance, both raise magnification M, making structures appear larger and changing image sharpness and artifact patterns, as shown in these fan beam CT reconstructions. On the right, we can see that adjusting either the detector or object position changes source to object distance and source to detector distance, which directly alters magnification and fan beam coverage, thus impacting resolution and image geometry in CT scans. Next, we will discuss magnification and spatial variance. Fan beam geometry has higher magnification at the center, which means finer sampling in the middle of the image. Also, a sharper image and sharper details. Rays at the edges are angled a bit more, causing increased geometric unsharpness near the periphery. In contrast, parallel beam CT uses constant magnification across the entire field. M is always equal to 1 in this case. This results in spatially uniform resolution with every point sampled at equal density. The diagrams show that fan beam magnifies the center while parallel beam keeps magnification and sampling the same everywhere. Magnification improves resolution centrally but creates spatial variance, which is the hallmark difference between fan and parallel geometries. The image to the right demonstrates parallel beam geometry, which keeps magnification M uniform across the field, while fan beam geometry increases M, which is directly related to the source to detector distance over source to object distance, thus causing central rays to be magnified and impacting image distortion. Next, we will discuss the quantitative validation of magnification difference. Full width at half maximum is the width of the point spread function at half of its maximum. In the parallel beam case, the full width at half maximum of the system's point spread function is usually spatially uniform across the image because the system geometry and sampling stay constant everywhere. This means the full width at half maximum value measured at the center is representative for the whole field. Only small changes across the image are observed. On the other hand, for fan beam, this image varies with position due to geometric magnification and spatially varying sampling density. Central rays experience higher magnification, producing a smaller full width at half maximum, which results in sharper detail, while the periphery has larger full width at half maximum, which results in more blur, because detector elements cover a wider region at more oblique angles. To the right, we see an image that demonstrates fan beam CT, which produces more variable full width at half maximum across the radius compared to that of a parallel beam CT, meaning that spatial resolution changes more with position in fan beam's geometry. Sampling density and Nyquist criterion are fundamentally linked in signal processing. The Nyquist criterion states that in order to reconstruct a continuous signal from its samples, the sampling density or sampling rate must be at least twice the highest frequency present in the signal. This minimum rate is called the Nyquist rate. Simulation to the right shows how angular sampling gets finer as theta decreases.
Up to this point, our blur came from sampling, but instruments themselves add blur too. Two key contributors are the focal spot size and the detector width delta D. For a fixed detector aperture, the projected width on the object plane scales with 1 over magnification. In parallel beam CT, M is constant. Blur is constant everywhere. In fan beam CT, M changes with position, so blur grows toward the periphery. On the MATLAB figure, the top Shep-Logan phantom demonstrates blurring as focal spot size increases. Notably, the fan beam reconstruction blurs more at the edges. However, the bottom phantom reconstructed with parallel geometry blurs uniformly as focal spot size increases. This loss of edge clarity corresponds to a drop in the modulation transfer function, MTF. We'll quantify that next. We next tested the effect of increasing detector element width delta D. In MATLAB, we used a Shep-Logan phantom. We saw that in parallel reconstructions, the blur increased uniformly across the image. In fan beam reconstructions, however, blur increased much faster at the edges. The MTF plot makes this clear. The x-axis is spatial frequency, how fine the detail is, and the y-axis is how much of that detail survives the imaging chain. Larger delta D lowers the entire MTF curve, meaning reduced sharpness. In parallel beam CT, the reduction is uniform. In fan beam CT, the change in magnification makes that reduction non-uniform. So magnification variation modulates detector blur, uniformly for parallel beams, but non-uniformly for fan beams. To correct the geometry distortion in fan beam data, we apply rebinning. Rebinning takes the measurements from the curved detector and remaps them onto a grid that matches a parallel beam geometry. When we compare direct fan beam reconstruction with its rebin version, angular sampling becomes more uniform. Notably, angular sampling increases in density and isocenter sampling becomes less concentrated. In combination, this creates more uniform resolution. After rebinning, the effective sampling grid changes. The true Nyquist frequency of the detector doesn't actually decrease, but because interpolation slightly smooths the data, the effective bandwidth is reduced. To preserve fine detail, we often need to sample more finely, which helps reduce artifacts, but can introduce slightly higher noise. To check rebinning fidelity, we reconstructed a 3-ring phantom in MATLAB and applied a direct fan beam, rebend, and parallel beam geometry. In the parallel beam vertical profiles, the impulses were uniformly distributed and symmetric. In the direct fan beam, the outer rings appear compressed and warped. The peripheral rings are visibly thinner. After rebending, the vertical intensity profiles of the fan beam and parallel beam reconstructions closely align. So rebending restores most of the sampling uniformity, but a small edge difference remains. In other words, rebending reduces fan beam resolution, non-uniformity, but it doesn't really eliminate it. Modern scanners further minimize this residual blur with smaller focal spots and advanced iterative reconstructions. To summarize, parallel beam CT provides uniform resolution, but is slow and inefficient. Fan beam CT enables fast full body coverage, but introduces spatial non-uniformity in sampling and reconstruction. Rebinning and modern algorithms compensate for most of that variation, leaving only minor edge degradation. Clinically, fan beam remains the standard because it trades a tiny loss in edge resolution for massive speed and coverage gains. Thank you.